Now we're going to get into actually talking about some types of organic molecules, and we'll start with saturated hydrocarbons. So a hydrocarbon, as the name implies, is any compound that's composed of only hydrogen and carbon. So there are a couple different types of hydrocarbons, a couple different classifications, but there's two main ones that we want to talk about: saturated and unsaturated hydrocarbons. And so what is saturated is the amount of hydrogen in the compound. The difference is that saturated hydrocarbons have no multiple bondings. There are only carbon-carbon single bonds. So that means functionally the carbon atoms are as maximally attached to hydrogen atoms as possible, whereas in an unsaturated carbon atom, there is multiple bonding. So for example, in this molecule right here, these carbon atoms are forming a double bond to each other, meaning they are not forming bonds to hydrogen atoms, right? That you could have more bonding to hydrogen atoms. So we're going to start talking about saturated hydrocarbons. We'll follow up with unsaturated in a later video. So when it comes to saturated hydrocarbons, every carbon atom has only single bonds, which means every carbon atom has 4 bonds, and they all have a tetrahedral arrangement, 109.5 bond angles. And so the simplest one is methane, where it's just 1 carbon atom bonded to 4 hydrogens. And these can grow bigger and bigger, where you get something, baby steps. Ethane, you get to 2 carbon atoms. They're still each bonded with 109.5 bond angles in that tetrahedral arrangement where all of the atoms are nice and spread out. As we get a bit longer and longer, we can see this idea where at the 109.5, the propane, we start to see this kind of zig that forms, zigzag. For a butane, it's 4 carbon atoms getting longer and longer. And so we could represent this in a condensed structural formula, which is just, plenty of CH3s and CH2s following each other. We can also start to see the representation in the line angle formula, and why we tend to see line angle formulas with bent lines like this, right? Where we have this zigzag that is representing the actual zigzag shape of the carbon atoms in a real molecule. That's why we have that zigzag idea, where in the line angle formula we have the zigzag shape or zigzag pattern, because that's representing the actual zigzag of carbon atoms that have that tetrahedral bonding arrangement. Even though the condensed formula shows them in a straight line, that's not really the shape. And again, line angle formulas don't have to show shape. It's not perfectly showing 3D shape, but it's kind of implying it, or kind of, might as well. So you can just keep forming longer and longer chains of alkanes by putting more and more hydrocarbons onto them, or more and more, carbon atoms into the hydrocarbon. And so these alkanes are just any sort of saturated hydrocarbon. It's called an alkane. And the ending for saturated hydrocarbons then is ane. If you remember, we said that functional groups determine naming. So you'll note all of these hydrocarbons up here all end in ane. So whenever we have a molecule that ends in ane, that tells us that it is a saturated hydrocarbon. It's an alkane. And so you'll note when we're looking at naming here, we kind of follow these conventions that for small, say 1 carbon is meth, 2 is eth, 3 is prop, and 4 is bute. Those names just kind of are historical for 1, 2, 3, or 4 carbon atoms. As we start to get to, say, 5 carbon atoms, it's called pentane, which is, the normal 5. 6 is hexane, 8 is octane, and so on and so on. We start, as you get to longer and longer chains, the naming follows the conventions to just indicate, well, how big is the molecule, how many carbon atoms are in there. So dec, like decade is 10 years. Decane has 10 carbon atoms.
Participation 12-2, question 2. What is the molecular formula of the following alkane? Got this line drawing down here. I want to know what is the molecular formula of that. This is the second question on participation 12-2, due Tuesday, December 2nd at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what is the molecular formula of the following alkane?
So while that kind of depiction, we only have shown, say, straight alkanes or straight chain alkanes, where they're just kind of the carbons are linked together in a row, you can have much more variety in the shapes of alkanes, where you have, say, branched alkanes, where instead of just, say, you have 5 carbon atoms in a row right here, and then one hanging off the side back over here. The CH3 that we have. And then you could also have things like cycloalkanes. Cyclo means cycle. So for example, you could have 4 in a row. So bute was for 4. And so you have 4 in a row. Cyclobutane. Pent, like a pentagon is 5. Well, pentane would be 5. And it's in a cycle. And so we can see we have these cycles, these ring structures that you can have in alkanes. So even though we have kind of this basic ingredients that in an alkane, in a hydrocarbon, it's just carbon and hydrogen, and in an alkane, it's just all single bonds, there's still a lot of flexibility with what those molecules can look like. Because carbon can form so many bonds, there's a lot of different structural kind of motifs and structural shapes that we could see in these molecules. So even though we have all of these different kind of structures, the properties of alkanes are still fairly uniform. One of their most important properties is that alkanes are very, very non-polar. We have this diagram here. This is what 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms long, so that would be an octane molecule. And it's showing all the dipoles cancel out. This is just kind of a diagram getting an idea, but really all of these hydrocarbon molecules are all very, very non-polar. And one of the most important attributes of that, or one of the important things that comes from that, is that alkanes are really insoluble in water. They really do not mix. Anytime you put alkanes and water together, you're going to get separation. They are immiscible. They do not come together at all. Another really important aspect of alkanes is that they are really unreactive. Carbon and hydrogen atoms, once they're in an organic molecule, they tend to not do a lot of chemistry. There's no real functional groups distinguishing this molecule, and so they just are really unreactive. Alkanes don't do a lot of kind of fine chemistry that we'll see as we kind of move through the other functional groups and talk about other types of molecules, where you can get sort of small changes, and instead they're just kind of unreactive. So another kind of their equivalent would be like water. So water is a polar solvent because water doesn't do a lot of chemistry, right? Water is very unreactive, so we use it as a polar solvent. So hexane is a liquid at room temperature. It's really nonpolar, really unreactive, so hexane is used as a nonpolar solvent. So if you do some heavy-duty industrial chemistry and you're doing, say, nonpolar reactions, you just get jugs of hexane or barrels of hexane that you can use as your nonpolar solvent. It's just a liquid, right? That's very nonpolar. If you want to dissolve other nonpolar things, hexane is a good choice. While alkanes do not do many sort of fine changes or small kind of changes that we're looking at in organic chemistry, they do burn really well. They're extremely flammable. This is one of the reasons, this is one of their main risk factors when working with alkanes in lab. They are extremely flammable. They evaporate really quickly. They make flammable fumes. Really not a good kind of, it really can be a really big problem in lab. But if you are in a situation where you want to create heat, say in combustion, so say gasoline in your car, you use isooctane, which is a particular isomer of octane that burns really efficiently and produces a lot of energy, a lot of good bang for your buck. Natural gas that we use to burn a lot of power, that we use in power plants, that we're using to power, most of, say, the electricity you're getting. Or if you have a gas stove, if you have gas to your house, you're burning that. Or say propane in a grill, you're burning alkanes and you're using the fact that you really can get a lot of bang for your buck. They are very, very flammable and very exothermic, their combustion, and very spontaneous because you also make a ton of gas. So you get it's both enthalpy and entropy wise, you really want to produce this reaction. It's very, very spontaneous. And so you get a lot really good bang for your buck. So this is not really the sort of fine organic synthesis, and sort of when we're going to be talking about organic reactions, normally we're looking at small changes to a molecule. Here you're taking this whole thing and just breaking all of the carbon atoms apart into CO2. So it's not really sort of fine or controlled. It's just kind of whole hog, just blow everything up up, really get a lot of energy out of it, which is fine if that's all you want. But when we're doing sort of organic synthesis or we want to look for small changes in molecules, fine control over what molecules look like, as opposed to just burn it up. But if you just want to burn some stuff, alkanes work real well.
All right, that was another video down with the participation question in it. There's only one more video left. Cool. See you there.